Good evening, students. Myself, Shamrat Paul. Now I am going to present a topic on sinusoidal pulse width modulation. It's a very important topic. And the short name, which is defined by, that is SPWM, means sinusoidal pulse width modulation. Here we are using the reference signal, that is sinusoidal wave. Okay, and we have taken the carrier signal just like previous classes which I had mentioned before, that is carrier. That is a carrier signal is suppose triangular, repetitive triangular signals. Same thing can happen. So first go to the waveform. Okay, see, this is the waveform for the appropriate triggering pulse which has to be applied for the purpose of sinusoidal pulse width modulation. Okay, it's a very interesting part. And why it is useful for industry application? This means that by using the appropriate triggering pulse, applying the sinusoidal pulse width modulation, the output voltage of the inverter, that is controlled in means that is regulated output voltage. That is why it is able to control the output voltage or the voltage control. As well as in this case we are using repetitive signal or triangular carrier signal, that is why for each half cycle number of peaks are so many times. That is why easily it can remove the unwanted harmonic and reduces the harmonics. As well as it is very important to implement for the industry purpose to improve power factor. That is why this is the several merits for using this control strategy for maintaining the appropriate gate pulse to the all switches. Okay, see, here we are using two signals, right? One is rectangular shaped carrier signal, okay, and the different one, that is reference signal, which is mentioned here. That is reference signal. And the carrier signal is rectangular shaped repetitive signal. Sorry, triangular shaped repetitive signal, means this is the triangular shaped carrier signal, repetitive in nature, okay, and which is bipolar, means it is having the positive half and the negative half. And in case of reference signal, we are using, suppose this signal is the sine signal which is defined by Vm sin omega t, and this is phase shifted 120 degree. This is called Vm sin omega t minus 120 degree. That means we can apply here, that is a two sinusoidal waveform and opposite in nature. And we have taken the complete cycle 0 to 2 pi. Okay, this one. And as we know, in case of pulse width modulation, the gate pulse that should be applied to the appropriate switch for inverter operation, that is G1 and G4. As G1 and G4, they are connected in series for inverter operation. That is why we never can apply the appropriate gate pulse to these respective switches at any instant, as it will provide the short circuit path. To avoid it, obviously the G1 should be applicable for the positive half for inverter operation, and suppose G4 should be applicable for the negative half of the inverter operation. That is why we have taken the two sinusoidal signal in the forward direction and in the negative direction, or in opposite direction. And we know this pulse has these pulses that have to be generated by the coincide point of the two signals, right, in this way or this way. It again the signal will be coincide. Where the signal will be coincide, it is the through which we can get the appropriate gate signal. Okay, now consider, so from this waveform, see, it is very clearful to us in the first case where we have taken this negative, this forward signal first. This means this signal first, this sine signal first, and first I am going to find out where they are coincide to the carrier signal, means this point, again these 2 points, these 2 point and these 2 point. That is why we have taken the pulse from this one to this one, as this is the first point coincide and this is the second coincide point. Okay, similarly again this point and this point, that is why it will provide these peaks, right? Again, so okay, similarly for the next case, again these 2 points are coincide by each other, right? Okay, that is why this is the starting point is this one and the ending point is this one. Again this peaks has generated. Again this point and the next is this point, that is why this peaks. Similarly again the starting point of the coincide, that is this point and this point, that is why this is a small peaks. Again these 2 point, this peaks, and there is these 2 points, that means this peaks. That means try to maintain your means order. If you will start from this point, then the next point will be ended here. Again suppose you will start from this point as the starting point, next will be this point. So in this way we will form the triggering, that means the gate pulse for the switch S1. So now for the second switch, sorry, now the second switch means the, I'm talking about the switch number 4, or the gate pulse is G4, then we should follow this waveform. Okay, again in this waveform where the coincides point with respect to the carrier signal or rectangular shaped signal, so first is this point and this point, that is why we have taken this is the pulse. Second is these 2 point, that is why this point. And similarly again it has coincide on this particular 2 points, so it will be this one. Similarly again go through this part, that means these 2 points are there, that is why this point and this point is there, that is why it will be the next peak. Again it will start from this point and here it will end it, that means the peaks is this one. Similarly we can draw the other peaks in this similar way. Okay, so ultimately we will get the 2 triggering pulse across the switch S1 and switch S4. Now as we know the output voltage that depends on, that is Vs into G1 minus G4, that means we are going to make this kind of possibilities, means G1 minus G4. That means what? This part minus this one. So in this, think about this particular region. In this region the peaks is this one, but no peaks is there. That means G1 minus G4, which will give you, this is the peak. Again G1, the peaks is this one, and for G4 the peaks is this one. That means this part minus this part, which will give you 0, as the amplitude of the peak and the width of the peak are same for G1 and G4. Similarly again you can think about this part and this part, then G1 minus G4 is this one. So in this way you can go through the positive half cycle and you will get this kind of peaks. They are almost symmetrical to each other. Okay, after pi what happened? Again we will do, that is G1 minus G4, that means this is the G1 and this is G4. So in this particular peak C, this part, right, and this part are same, that is why it will give you 0. But see, in this case there is a 0 next part, but here the peaks is this one. That means what? That means, as we know, that is G1 minus G4, that means 0 minus this one, so it will give you this peak. So the peaks is maintaining in negative cycle and in opposite direction with respect to the previous one. Clear? So similarly, through the same way we can say, now if this is G1 and this is suppose G4, so that means this part is negative, this is, and this part reflected on the negative part, and these two are maintain 0. Again, so go through the next half cycle. So you will get this kind of pulse for triggering the gate pulse, so triggering the gate of the respective switches. So see, in this particular case, as we are using the bidirectional carrier signal, okay, suppose when the G1 stops working, then the G4 starts working. If there is any delay which is inputted due to some uneven condition, then if G1 starts working, then on this particular instant, suppose G1 is in on state. That means immediately then G1 and G4 will be short circuited. Okay, so to avoid it, we can use this kind of signal also. Okay, that means, and as well as we can avoid the number of signals. In the first case, as we are implemented, the number of the carrier signal is bidirectional in nature. That is why we should be implemented the bidirectional sine wave also. If we can produce, this is a kind of carrier signal, maybe this is suppose this can be implemented for the forward direction, and it is supposed implemented for the reverse direction or negative direction, then automatically we can apply only one sine wave over here. That is why we can minimize the number of sine wave. Okay, so this is another pattern. But now we are going to calculate, that is, so from this above discussion we can conclude, that is, instead of maintaining the width of the all pulses the same as the case of the multiple pulse width modulation that I had discussed in the previous section, the width of the each pulses is varied in protection of the amplitude of the sine wave. The gating signal are generated by comparing of the sinusoidal reference signal with a triangular carrier signal of the frequency of Fc. The frequency of the reference signal Fr determines the inverter output voltage frequency, that is F0, and its peak amplitude AR controls the modulation index, which is defined by M, and then in turn of the RMS output voltage V0, comparing the bidirectional carrier signal VCR with, and the next section will be repeated for the next sheet here. See, that means the sinusoid, that means we can say two sinusoidal reference signal VR and minus VR, this produces the gating pulse, that is G1 and G4. However, G1 and G4 can be generated at the same time. Then the number of pulses per cycle depends on the carrier frequency. Within this constraint, then the two switches may be on in the same instant, then S1 and S4 then can be conducted at the same time. The same gating signal can be generated by using unidirectional unidirectional triangular carrier wave. Just I have discussed before, so this is the conclusion part. Okay, that is why. And now if we are trying to maintain the uniformly pulse width in case of the gating pulse, then the sine wave can be replaced by triangular shaped waveform, that is reference signal. Then the every coincide point will be remaining same, then it will produces the same amount of width of the pulses, the appropriate G1 and G4. That means what? I have discussed so many things, just keep it in your mind. If we are using the sinusoidal, then as well as the sinusoidal wave for the reference signal, then we should implement the carrier signal, that is repetitive triangular waveform, and which is bipolar. Okay, so in this particular case we are using two sinusoidal wave. Suppose we require one sinusoidal wave, then what happen? Then we can change the waveform like this one, then the carrier signal waveform can be changed. Then we are not using the bipolar carrier signal. Here we are using the unipolar carrier signal for this one and for this one. That means we can avoid the other reference signal, other sine wave. Okay, so this is the one advantage for using this kind of carrier signal. Different one maybe in case of the sine wave, or depending on the amplitude of the sine wave, the pulse width can be changed, right? So maybe a tendency to make somehow any delay can be inputted for some abnormal cases during operation of the inverter. Then G1 and G4 means the switch S1 and S4 can be short circuited by each other. Okay, to avoid it, to provide the appropriate width of the pulse to the gate or to the appropriate switch, we can replace the sine wave by the rectangular reference signal. Okay, so this is the conclusion part. Now go to the calculation of RMS value. This is well defined by here, that is VRMS equal to Vs into summation of this one. That means what? Here the Vs into M equal to, which is M means, that is mth, means the mth order. So it is clear to implement this method and is preferably okay, and so it is clear to implement this method and preferable. That means I am talking about the previous section. Now see, the algorithm for generating the gating signal is similar to that for the unipolar PWM, except the reference signal is sine wave, that is VR equal to capital VR sine omega t. Instead of DC signal, the output voltage is V0 equal to Vs into G1 minus G4. So just I told you before this one. This is a previous section, just I discussed you before the few minutes back. Now see, if delta M is the width of the mth pulse, so RMS output voltage can be written as VRMS, this one. That means delta M is the width of the mth pulse. Okay, suppose we consider the any pulse for the mth mth number, then we know if the pulse is suppose this one and this is the width is suppose delta M, which is depicted on the waveform. See, here we mention the pulse width, that is suppose delta M. Okay, I don't know what is the width of the pulse, so assume this is a mth number of pulse, mth number. This is defined by M. It can be happen for this one, it can be happen for this one. That is why this is the mth number of pulse which is having the width of, that is delta M. So this is only defined by the expression this one. Okay, that means mth. If M equal, that can be continued from the first pulse to onward, that is M equal to 1 to 2p. Why the term stands for 2p? 2p means, that is p means the number of pulse, okay, in one half cycle. So if we consider total period, that is defined by the 2 half cycle, that is 0 to pi 0 to t by 2 and t by 2 to t. That means what? The number of peaks is actually double for the first half cycle and for the second half cycle, that is defined by 2p. So the RMS value is defined by Vs into M equal to 1 to 2p, means any number of peaks we can assume or pulse we can assume, and the width of the pulse is, that is delta M by pi, that is under root. So this is the calculation for the RMS value. Okay, where this RMS value had calculated for the multiple pulse width modulation. So the similar approach already I have discussed here. So this is all about for the sinusoidal pulse width modulation. It's a very important topic. Okay, please go through the topic. So thank you students.